In this section, 8.2, we're going to connect the translational motion with the rotational. First, let's remind ourselves how we set up our rotational motion. We said, okay, this is a distance along here of S. This is a distance R, the radius. And this measures an angle theta. And theta is defined by the change in S over the change in R, or S divided by R. That defines what our angular velocity, our angular position is, and that is in terms of radians. Then we looked at how this could change if this object were moving, and we got an angular velocity, which was change in theta over change in time. And this, of course, is radians per second, and this is called angular velocity. This is angular position. Then we had the angular acceleration, which is change in omega over change in time. In other words, how fast this changes, or equivalently, the second derivative of theta with respect to time. Now, if you are not familiar with the calculus, of course, this is just the change in theta over the change in time, and this is the change in omega over the change in time. Well, these are the equations that we had and the definitions, and they correspond to position, velocity, and acceleration in angular sense. We now want to relate those to translation. And the first thing that we notice is that this distance S along here can be thought of as R times theta. So we're going to take S as being R times theta. And now we're going to take the derivative of both sides. So ds dt, since R is constant, is R d theta dt. And we immediately see this is the tangential velocity. So the velocity tangential, it's a particle like a bug that's riding on this wheel that's spinning. He will feel a velocity, which is R times omega. So now we've been able to relate omega to the velocity, just like we've related theta to a distance. Now, if we take the derivative of this, then we look at the change in the tangential velocity. If the tangential velocity gets larger or smaller, with respect to time, it would be R times d omega dt, or equivalently, A tangential is going to be equal to R times alpha. And now we have related angular acceleration to the tangential acceleration over here. Well, if our angular velocity is constant, our angular acceleration is constant, let's assume that this is true for a moment and see what happens. Let alpha equal to a constant. That means it's speeding up or slowing down at a uniform rate. This might be a cyclist who's pedaling along and he decides to slightly put on his brakes. And so he puts on his brakes, or maybe he just coasts for a while. So he's gradually slowing down. That gives him some deacceleration, so alpha would be negative. Just like when you deaccelerate a car, the acceleration itself is a negative value. That's what the brake does. Okay, so if alpha is equal to a constant, then working from this equation here, we see that d omega is going to be equal to alpha times dt. Well, since alpha is a constant, we can integrate both sides. The integral moves inside, and we get from 0 to t, we get alpha times t omega minus omega naught. It's from omega to omega naught. Or omega is equal to omega naught plus alpha times t. Well, that's exactly comparable to what we had when we said velocity is equal to V naught plus A times T. Now we can take that one step further and we know what this is. This is d theta dt, and that's going to equal to omega naught plus alpha alpha times t. So multiplying through by dt and integrating, we get the integral of d theta from 0 to theta, say, is equal to the integral of omega naught dt plus the integral of alpha t dt. Well, this is a constant that comes outside, so this is omega naught times t. This is going to be theta minus theta naught, because I've got two limits there. And this integral is going to go from, again, 0t up to t. That's equal to alpha plus alpha, which is this term here. And the integral of t dt, as you recall, is t squared over 2. So this is going to be t squared over 2. Therefore, we can say that theta is equal to theta naught plus omega naught t plus 1/2 alpha times t squared. This is exactly the same as the equation for position, just as this is for velocity. So this equation is comparable to our old friend v is equal to v naught plus acceleration times time. This is comparable to x is equal to x naught plus v naught t plus 1/2 a t squared. And because of that, we remember we solved these two equations to eliminate the time, solving this one for time and substituting it in here. And we got a really neat equation. You recall what that equation is? That equation was v squared minus v naught squared is equal to twice the acceleration times the distance. That was very nice because it does not involve the time. So we could see that if you drop something off of a building of a certain height, what would its velocity be at the bottom and so forth. Well, the exact same math obtains here. And we can therefore eliminate this, solve this for t, substitute it in here and simplify it. And what we'll get is omega squared minus omega naught squared is equal to twice the alpha, not a, but alpha, times distance, and that would be your theta. And that's the comparable formula for rotational motion to what we've had for translational motion. Now, all of the equations that we have used in solving for this one, and this one, there's three equations in kinematics for translation, can now be solved using these. To work some examples of what those problems might be, I'll work a couple of simple ones. We could imagine that we have a bicycle tire, and it goes around as this person is traveling in, let's say, this direction. Let's assume you're traveling with a certain velocity, v. How do I relate that to all these other equations? Here my bicycle wheel is turning. Well, for the person sitting on the bicycle, this point is not moving with velocity v. It's the road that's traveling in the other direction with a velocity v. Since the road touches the tangent to the wheel, it follows that v is the tangential velocity of the wheel relative to the center. Well, that really helps because therefore the velocity of the bicycle is equal to the velocity tangential. And now, knowing the tangential velocity, we can find omega. How do we do that? Well, let's say that you're traveling along at 10 meters per second, and that's your tangential velocity. We ask, first of all, what is omega? That would be a typical test question. Well, omega is going to be equal from this equation right here to the tangential velocity divided by r. Well, I have to give you the radius of the wheel. Let's say the radius r is equal to 1/2 of a meter. So what we would end up with here is the tangential velocity, which is 10 meters per second, divided by, that's seconds there, divided by r, and r is 1/2 meter, so it's 20, and that's radians per second. And that would give us our omega. Now let's suppose that we take this bicycle and we stop it. And we stop it in a time of 4 seconds. Delta t is 4 seconds. Then alpha is going to equal to what? The change in omega over the change in time. Well, what's the change in omega? Well, I was going 20 radians per second, and I'm going to go down to 0, so the difference is 20 radians per second minus 0, so I can leave that out, divided by a time of 4 seconds. So the answer is 5 radians per second, 5 radians squared. Now once we do that, we can move through all the angular velocity. We can say how far did it go while you were stopping. Let's say if you began applying the brakes at time t is equal to 0, and you went down to an angular velocity of 0 from an original angular velocity of 10, tangential velocity of 10 meters per second, angular velocity of 20 radians per second. How long would that take? How far would you go? You could solve it this way or this way. And let's just work that. How far did this person go? Well, you'll notice that from right here, their angular acceleration is going to be equal to, I didn't write it out here, that's equal to alpha, that's 5. Radians per second squared. So we know alpha is equal to 5. We know the original omega, omega naught, is equal to 20. And so what we can do is compute something like how far did it go? So we'd have omega squared minus omega naught squared is equal to 2 alpha times theta. How far did it go? How much did it turn? The answer is it stopped finally, so this is 0, minus omega naught squared, so it'd be 20 squared. That's going to equal to twice alpha, and alpha is 5, times theta. So 5 and 5 is 10, and this is a deceleration, you'll notice, so that actually has a negative sign that cancels this one. So that's 10 into 400, so that's 400 over minus 10, so that's 40 for theta. Well, how far did it go along the ground? Well, if we know the radius, then is a half a meter, then we can use that with this formula here to say how much space did it cover. And S is equal to R times theta. Theta is now given by, let's see, what do we say? Yep. Theta is going to be given by 40, because I had 20 squared, which is 400 divided by 10, so that's 40 radians. If I have 40 radians, then I can say that the distance S is going to be equal to R, which is 1/2 a meter, times 40 radians. So the answer is 20 meters. Very simple. Oh, I let the paper slide there a little bit.